I should mention that my talk oriented on students. I prepare it for students and for young scientists. So maybe someone will find it simple for them. But I will orient on the students at the first place. So, okay. Куда? Сюда. Так я жму. Ну, я на стрелке. Сейчас. Let me. No action. So, okay. Here is the outline of my talk. And I am going to tell you something about motivation, and then about methods, basis sets, maybe some other interesting features of these calculations. I will tell you a few words about software, and maybe show you some examples which include simple systems, not some difficult and big systems. And I will make the conclusive remarks. Okay, let's go to motivation. I have 3 points about motivation. At first, I want just for people to understand these kind of abbreviations, because when we phrase quantum chemistry, we will have many such abbreviations, acronyms. Here is letters, numbers. It's all mixed, and many people don't know at all what is this about. Then the second point of my motivation of this talk is that once I met a scientist, and when he heard just a word, quantum chemistry, he almost began to pray on this word. It's like a god. But I want to tell you that these methods, they are efficient, they are powerful, they are interesting. They are difficult, yes, especially computationally difficult. But surely they are not divine. And at last, I want to cite this short story about football. This story, one of my teachers, Professor Vadim Malnev, he liked to tell this story to his students. When young goalkeepers, before a match, he says, I will save all difficult shots. But his coach say, you'd better save easy ones. And there might not be difficult shots at all in this game. So our main goal, we shall try to save easy shots in this talk. Okay, I will start from the beginning. And at the beginning here, I will tell you about variational principle. Variational principle is principle which allow us to evaluate energy for some Hamiltonian using trial wave function. In simple, we can put down this and say that we got some value of energy, and variational principle gives us energies from above. This will be, so our trial energy which we gain will be upper than exact one, always upper. This is the variational principle. If we know exact wave function, so we gain exact energy.
In this case, we will have equality. So
yes, equality here. Yes. We can update this using some parameters. I call them A in trial wave functions. And we can additionally minimize our energy by these parameters. It will be more powerful. But we can use our trial wave function as some expansion of some basis. And in this case, these coefficients of this expansion, they will be our variational parameters. We can write matrix elements, and we will gain this kind of problem. This is a generalized eigenvalue problem in linear algebra. And what can we get from here? From here, when we solve this, we can gain, if it is n dimension, yes, we can gain n energies. And for each of these energy, we will gain this column, this set of coefficients. When we find the lowest value of energy will be our ground state. And for it, we have a set of coefficients and a function which gives us this state. This method also allows us to calculate excited states. We can do this. In nuclear physics, once we used such a scheme, but we also used nonlinear parameters for which we minimize this energy. It was a more complicated method, but this is another science. And I want to emphasize that Rayleigh and Ritz, this man contributed into this theory, and many other scientists, physicists, mathematicians, even Nicola Bogolyubov, he also used variational methods in his work. Okay, then let's go to Hamiltonian of our of molecular system. Molecular system consists of electrons and nuclei with such coordinates. We construct this Hamiltonian. As you see here, terms kinetic energy of electrons, of nuclei, attraction between electrons and nucleus, a term about nucleus repulsion, and electron repulsion, Coulombic terms. And this is, as you see, this is complicated, very complicated problem. And how to solve this problem? And here we can remember, as they said in Middle Ages, this principle, divide and conquer, or maybe in antique times even, divide and conquer. But what shall we divide here? At first, these good men, Oppenheimer and Born, they proposed, and this is, I think, maybe this is obvious, that let's separate nuclear and electronic motions. Let our wave function be the product of nuclear part and electronic part. And what can I say about this? This approximation is reasonable. It is good approximation because our nuclei are much heavier and move much slowly than electrons. We can do this. Only in some very particular cases, this approach will not work. So we killed a term with kinetic energy of nuclei. And we can write electronic Hamiltonian in such form. And for this electronic Hamiltonian, we will have such a Schrödinger equation where this parameter R, nuclear coordinates, they enter here as a parameter, not as a variable, but parameter which we know, it is fixed and known, but it enters as a parameter. And also I should mention that this effective energy will define potential energy surface. I will talk about this later. And okay, but the problem remains difficult. What to do next? We cannot solve this. Then came Hartree and he said, let each electron be independent. Let our electron wave function be a product of n single electron wave function. So each electron will feel only some effective interaction from other electrons. Not direct, but some effective. But this approximation is not well justified. And somebody even said that this is a crime. But because electrons here are not correlated, and to neglect electron correlation is not so good. But okay, Hartree said, let us proceed with this. But they don't know what to do with this function. And then Fock said that this function must satisfy antisymmetry. It must be antisymmetric for permutation of two fermions, as you know, because electrons we have, and to satisfy Pauli principle. And he said, let this function have the form of this determinant. And as a determinant, you can see if you permute two rows, you will have change in, you will have minus determinant, yes? And Pauli principle, if two rows are similar, then our determinant will be 0. So this satisfied in so-called, this structure is called Slater determinant. It was invented by Slater. And the constituents of this, let us call them spin orbitals. I will tell slightly later what is this, but let us call. And let us propose that this is our trial wave function for variational principle. If we use this as a trial wave function, we will gain a set of equations for this single spin orbitals. With this operator, which is called the Fock operator, you can see here, it also includes this effective interaction, which means J is a Coulomb operator as average. It is of classic origin. It is classical electron-electron repulsion. It's its origin. And K operator, which has fully quantum origin. It is about antisymmetry. This system, this what I said, spin orbit. What is spin orbital? Spin orbital is function which can describe everything for one electron. So its position and its spin state. It can be divided as a coordinate part and spin part. Spin part is alpha and beta. This means alpha is spin up, beta is spin down. So if we have one coordinate spatial orbital can be occupied by two electrons, one up, one down. And also I should say that these molecular orbitals, they will describe an electronic structure of our molecule. So electrons in our molecule will be placed on some orbitals and so on. And for atoms, we must build these molecular orbitals as a combination of atomic orbitals. This is called by this abbreviation MOSLCAO, molecular orbital as a linear combination of atomic orbitals. If we write such an expansion, we can see that we have these coefficients, and coefficients can be, as I said in the starting about variational principle, can be natural parameters for optimization. And okay, and I will say that in these calculations, in these methods, these atomic orbitals, this set of combination of atoms, it is our basis set. But I will tell later about basis set. So we will take this function. Yes, this function enters here, this psi, it is in Slater determinant, yes. To gain systems full wave function, we must place this into Slater. Slater determinant is our wave function of system. Yes, but this is further expansion, how to say, further simplification, or maybe expansion, let's say. We will gain, with these functions, we will gain a system of equations. Here you can see this system with some matrix elements. Here I put some formulas, but essential, I can say this D. It enters into so-called Fock matrix here, and it depends on coefficients of this expansion. And this problem, we can see this system of equation is called the Ruth-Hall equation. We have such a form, and we can say that this is, again, our good eigenvalue problem. But here, we can say that this pseudo-eigenvalue problem. Why? Because Fock matrix, this F here, when we construct Fock matrix, we use this density matrix, and density matrix depends on coefficients from expansion. And here we have coefficients. So we must, we put here coefficients, and we gain again coefficient. So what is, how to solve this? To solve this, we must use so-called self-consistent field. This is a method or how procedure, self-SCF procedure. What do we do? It is iterative method to solve this problem. What should we do? We shall make some initial guess of starting coefficients, then build Fock matrix F. Then solve these equations. Solve, I mean, we gain energies, these epsilons, and for each energy, a set of new coefficients, new set of coefficients. Then, with new coefficients, we construct again density matrix and check convergence. What is check convergence? There is some criterion, and we say if a new density matrix is significantly different from old density matrix. And if it is different, we say convergence are not achieved, are not reached. And we say no, and we begin again, but with new coefficients here, this loop we perform. And we must do this sometimes, this cycle, and when we check, you can check convergence by energy again. If energy does not change significantly, we can say that convergence is reached. And when convergence is reached, we come to result. And what is result in this case? The result is we perform a solution of this equation. We gain coefficients and orbital energies for our molecular orbitals. We can construct them and know their energies. We can construct spin orbitals occupied by, from them we go to our Slater determinant, and from Slater determinant we have approximate solution of Schrödinger equation. It's what we wanted. Also, I should mention here, that when we expand our molecular orbital, we expand it on basis, and basis has m functions. And m is bigger than n number of electrons. So as a result, we will have some unoccupied orbitals, which we call virtual orbitals. They does not contribute in total energy, but they can be very useful. So, okay, but now let us, I will save some brief report about what to do with Hartree-Fock to correlate electrons lesser than number of bases, than dimension of bases, yes. Yes, we will have orbitals, more orbital, we will have unoccupied, yes. There will be free, how to say, unoccupied, yes. But let us remember that we made assumption when we talk about, when we divide our wave function to single electron product, that we neglect electron correlation. And so the Hartree-Fock results, they are good, but they are significantly, they have some significant, how to say, problems, yes? And scientists wanted to update this. They tried to insert here electron-electron correlation here. And they wanted to insert it as some addition to Hartree-Fock result. And there were produced some new methods, which is called, or post-Hartree-Fock they call, or they called correlated method. I will tell you brief, because every method, it needs much time to explain, and I don't know some of them so good. But let us say, there is configuration interaction method. It bases on a combination of many configurations, so our later determine. And to represent constant molecular orbital. It is variational. What I mean variational is that energy, energy that we gain from this will be upper evaluation of true energy, of exact energy. Also here is complete active space, SCF. Yes, it is variation. Well-known NPN scheme. It is a Möller-Pölzer perturbation theory of nth order. You can meet this many times in different works, especially MP2, second order of this perturbation theory. It bases on expansion of electronic Hamiltonian, and this Fock operator is zeroth order of this expansion. This method is non-variational. It will not give us this energy. It will be some energy. We cannot say that it is upper. And also there is a method called coupled cluster. And of course I can here put the CCSDT. You see, this is a long abbreviation. And this method is called golden standard in quantum chemistry. This is a very powerful method, very accurate. But it is, as you see, it is very costly. Here we can, this is just a simple evaluation, maybe it is not so correct. If we take a Hartree-Fock calculation for one point of time, then MP2 is something like tenfold of this, and you can see another method in time. Okay, let us, and also I want to add that all these schemes I present in calculative software, this all is automated. So we don't need to construct these matrices to minimize these parameters. It is all, but I tell you about this just for you to know how it works there in the inside. How it works, yes. Okay, there another different method of calculation is so-called density functional theory. What is then here is completely another ideology in this method. When standard quantum mechanics, it is based on wave function. The DFT is based on electron density. And what is a difference between these? We can say that wave function is uninterpretable, essentially. So we know that we can this square and integrals, and it is an amplitude of probability, but electron density is physically observable value. And also we can say that wave function in quantum mechanics, it depends on coordinates of all electrons. But our density depends only of 3 coordinates. And we can write, what is density? Density can be written as this integral. of function. It is probability to
Ma
find.
è una lezione normale di praticamente tutto così struttura della materia, c'è tutta DFT. Sì, ha fatto tutto quanto. Adesso ci sono con e Sham.
Okay, Zaira.
Okay, this is the probability to find the electron on some distance in our system, yes, from nucleus. This man, Kohn, Hogenberg, they proposed some theorems. And these theorems they call existence theorem and variational theorem. These theorems, they say that ground state properties of many electron systems are uniquely determined but by electron density. And variational theorem, it says that there exists a variational principle. The true ground state density minimizes the total energy function. So if we know true electron density, we know true energy, true ground state energy of our system. But we can say that these theorems, as they say, it is powerful, but they do not offer any practical method. It's just theorems. What to do on practice? On practice, Kohn and Sham, yes, they received the Nobel Prize. Kohn, maybe, I don't know about Hogenberg, maybe yes. Kohn, yes, Kohn, yes. And how to solve this, how to implement this theory into our system? They say, Kohn and Sham, they say, let us take as a starting point some fictitious system of non-interacting electrons. But overall ground state electron density is exactly the same as for the real system. So we replace interacting system with some fictitious non-interacting system having the same density. And our energy will be written as this. Here, first three terms will be for non-interacting electron, and all that concerns interactions, correlations, this delta in kinetic energy, it is delta between kinetic energy of non-interacting and interacting system. And we can put here, everything we don't know. So here it is simple non-interacting, and everything which is more than this, we can put here. Yes. And here, we can put everything, corrections, exchange, and these terms are called, they give us so-called exchange correlation energy. I will tell about this. And then we can introduce, again, fictitious spin orbitals in form of Slater's determinant, again, as it was in Hartree-Fock. But here, these spin orbitals, they have no such meaning as molecular orbitals in Hartree-Fock. They are just used to reproduce density. And they are used mainly as a computation, more computational tools. And again, the same scheme as was in Hartree-Fock, but with another values, of course. And here we can see this exchange correlation term. It will be here. And we will go, again, we perform this molecular orbital as linear combination of atomic orbital expansion. We imply our basis. And we gain a set of equations. We call them Kohn-Sham equations. And they are very generally similar to Hartree-Fock, not in quantity, just. And we can solve them, again, with analogous self-consistent field procedure. But here will be our electronic density function and this Kohn-Sham matrix. So we guess initial density matrix. Density matrix is determined by our spin orbitals. Yes, and it includes coefficients of expansion. We build constraint matrix, we solve that system, we construct new density, functional, not metric. We check convergence, and again, we perform this loop, or if convergence is reached, we go to result. And what should I say to compare Hartree-Fock DFT in this computational way? They say that Hartree-Fock is approximate theory because we made assumptions, but development of that theory was motivated by an ability to solve all equations exactly. And when we speak about DFT, they say that this is an exact theory. But all equations are solved approximately because we don't know exchange correlation energy. It is that what we have here. We don't know the form of this. So this is again approximate method. And what about exchange correlation energy? Exchange correlation functional. We must find it. And how can we find it? And scientists begin to propose their versions different because it is critical part of DFT. It describes, as I said, the difference between classical and quantum mechanical electron-electron repulsion, different in kinetic energy between non-interacting and interacting system, or real system, yes. And people propose, scientists propose some variants of this functional. First was local density approximation with this abbreviation. You can meet these abbreviations in your calculation software. This depends only on the local density. Generalized gradient approximation adds to this gradient from electron density. And here is some examples. BLIP, LYP, PBE. Also, there are functionals, which includes Laplacian. They are more flexible. There is some examples. Hybrid theory. And here we see our well-known B3 LYP or B3 LEAP functional. This is widely used in calculation. You can meet this everywhere in literature. Almost everywhere. It mixes some part of exact exchange from Hartree-Fock theory with generalized gradient approximation. And there are double hybrids and other functionals. And I must emphasize that the right choice of this functional determines the properties of the quality of our calculation. So we must choose wisely this function. Okay, I will move to basis sets. As I said earlier, all methods are based on expansion by basis set. What should we demand from our basis set? Our basis set must be as minimal as possible because there can be very difficult calculations, and when we take for some small system some large basis, it is unnecessary to do this. So we must try to keep it minimum. Then the next, our basis, its form must be convenient for integrations. And the third part, our basis set must represent it must be realistic. To represent, its form must be chosen to have some chemical, physical sense. There are two widespread types. Slater type orbitals and Gaussian type orbitals. Slater type orbitals is exponential form, you see. Gaussian is a Gauss form. This Slater type orbital, this is more accurate from a physical point, because we can remember our functions for hydrogen atom and this. And also it have good short and long range behavior, good physically, you can say. But Slater type orbitals are difficult for integration, and so they are rarely used directly in practice methods. But Gaussian type orbitals, because of this Gaussian form, it degrades with distance many more faster than this. And this, because of this, it has poor physical accuracy, poor short and long range behavior. And we can try and represent this orbital with Gaussian type. But we must combine some Gaussians as a sum of this function. We can try to represent some features of Slater type orbit. So we must combine some of them. But this is fast and efficient with these functions. And so every basis, not every, but the most basis set uses a GTO, Gaussian type orbital. And if you wish, I can ask students, can they they should think and tell me why Gaussian type orbitals are better than Slater type orbitals in case of integration. Okay, I will tell you something about basis sets which are used in calculation methods. The first is so-called minimal basis set, is we call this abbreviation STO 3G minimal. What does it mean? It doesn't mean that here in this basis we use three Gaussian functions to represent, trying to represent Slater type orbital by 3 or by n, 2 or 6 maybe. But this basis is good for only light evaluations, for maybe large molecules when we cannot apply some, we have no computational power to calculate, just a simple basis for some evaluation only. Then comes the Popple basis sets, or they are called also split valence. They include, you can see this,
що справді зараз, можливо, наступила епоха цієї щирої відкритості, нібито, і це може поставити.
Я перепрошую, ви маєте питання? Okay, let's continue.
This abbreviation, NM11G or NM1G, is double zeta, because two functions added to valence orbital. Triple zeta is three basis functions here. Also, I should tell you this, that our functions, not just we add one primitive Gaussian, but we can present one basis function, as a combination of primitive Gaussian. So this N means core orbital, and it is, for example, 3 or 6 usually. I will show you here, something like that. This means that our core orbital constructed of one basis function, which constructed of 6 as a combination of 6 primitive Gaussian here. So these numbers you can see, and for students I will tell that it is interesting to take some molecular and try to reconstruct number of functions, a number of primitives for this molecular. They are all Gaussians.
Yeah, I know. I understand, but this is the sum of
Yes. Some it is like expansion, like basis set, but sum of basis function can be constructed of more than one Gaussian. Six core for core, we have six here. If we have, you know, this basis 6, 3, 1, G, for example. Primitive Gaussian in this form for higher angular momentum, we can have not one function. As you see here, you can put one, for example. Here you can see 3 functions will be. One here, or one here, or one here. There is also polarization functions added to our basis sets. And they can be noted like this, or in more general as with this parenthesis, like this. And what does it mean? It means that the first number here, what is a polarization function? Polarization function is when we add to our basis a function of higher angular momentum. So we can add D function. Of higher, our molecule may not have electrons with such a momentum, but we by hands insert it to better describe some properties of the system. It can be necessary for many cases. So this, and also we can add diffuse functions. We mark by pluses here. If one plus is used, it's to all non-hydrogen atoms. What is diffuse function? Diffuse function is a function with very small exponent. It is widespread Gaussian. If 2 pluses, then this means that to all atoms, to hydrogens as well. Also, there is a good basis set constructed by Dunning. It has this abbreviation. And this basis set was constructed specially for correlated quantum chemistry calculations. So it is good to use such kind of basis with methods like MP, Möller-Plesset, or coupled cluster. Here is a construction. Diffuse function is augmented basis, and again, there are other basis sets, many of them, or some old basis sets, some interesting basis sets which we must use when we calculate heavy atoms, very heavy atoms. And you can find many basis sets on this site, and you can see their properties. It is good, good to visit. And then I will tell you just a small, briefly about some other topics, such as, let it be solvent model. Our computation with quantum chemistry methods, we can use solvent model. So we can place our system in solvent. But how to do this? Solvent can be added explicitly. It's when we use molecules. When we put molecules of solvent, but this is computationally expensive, as you see. We put molecules of water around, and this is it. But we also have a possibility to use implicit solvent models. Implicit solvent model is, for example, polarizable continuum model is well-known PCM model. It is also widely used, or it's other variants like conductor, like integral equation formalism. And this implicit model, they treat our solvent as a continuous dielectric medium surrounding the cavity where our molecule is placed. And to perform more realistic calculation, we can use, for example, water in PCM model. We can use continuum of ethanol, maybe. There are many possibilities for this. And also, I should mention some problem when we have to calculate interaction energy of some complex, which consists of molecular A and molecular B, or object A and object B. What is interaction energy? In the simplest way, as a supermolecular approach, It is a difference between energy of total system and energies of its constituents. But here we will need so-called basis set. When we calculate this quantum chemically, we will face so-called basis set superposition error. What is this? It is say that when we calculate energy of A independently, our basis for this system is centered on system A. When we calculate system B, our basis set is centered on basis B. We construct bases, like I said earlier, for these and for these. And when we calculate system A and B, basis set is centered on full system. And it will be larger for full systems than for constituent systems when we calculate them independently. So this value will be larger than this. And we will have overestimation of energy. For these scientists, they made so-called CP correction, counterpoise correction. This is procedure, it inserts automatically in calculation. You can insert it. And it counts every of this energy in this basis. So we must calculate, to make a good difference, we must calculate everything in one basis, not in A-centered basis, B-centered basis, and total system. Okay, we have our difference as CP corrected, yes. But also, if our objects, molecules, constituents are deformed, when they are deformed, this may have influence on our energy. So we must insert so-called term as deformation energy. Deformation energy is difference between energy of this molecular in complex. It have some geometry in complex. And it may have another geometry when it is isolated. Another ground state geometry, another optimal geometry. So we must do this difference. And our full interaction energy will be like this. CP corrected delta and some term of deformation. And of course, I must tell you something about software packages. Here is just briefly. You know all this. Gaussian, Orca, Games, and many more good packages, many more software. But what I should emphasize? I should emphasize that Gaussian is good. All methods are good, especially for some general tasks. For some complicated, maybe you should know you should read tutorials or documents. But for general tasks, they're good. But Gaussian, it is commercial. And this company of Gaussian, they are known for extreme paranoia. So if you use Gaussian, please use it very carefully. Because these people, they can ban almost everybody. They ban even people once. They ban universities, they ban institutions, they ban organizations, people. This is an extreme group of people, this Gaussian Incorporated. So be careful with this. And of course, don't use pirate software, because they will know and they will find you. Orca, people say that this is good. And also, as Alexei a year ago talked, that Orca is integrated into QMMM schemes. Orca is good and it is free for academic use. Games and other. So you should choose wisely. So I have some small time. I will show you some just examples. They are very simple because here we just perform some methods to small objects like water molecule, hydrogen peroxide molecule, and some other. You can see details in these works, but it is not so necessary. I can see what is a peroxide molecule. Peroxide molecule is a molecule much like water, but I think it is better than water in case of training, in case of training in quantum chemistry, because it has this dihedral angle. And this dihedral angle is very sensitive to changes in medium. You see here we can optimal geometry of this is method DFT B3 leap, and B3 leap using PCM model of water solution. You can see everything almost unchanged, but dihedral angle changes significantly. For water, it is not so. And also here I presented number of functions of bases used, 56, and here you can, I recommend you to calculate just for yourself. Choose some molecule and try to calculate how many basis function in some form of basis, how many primitives there. Also, we can calculate something like sodium ion with phosphate group, and we can see that this in a PCM model gives this as a better, as an optimal energy. And this is very good because we can see this distance here. And this distance we can gain from a molecular dynamics simulation of some system, which includes phosphate and sodium counterion. Exactly this distance will be. And some other consideration. Here we can see deformed significantly. This is some toy systems. This is not some great physics here. But we can see how peroxide molecule can be deformed significantly. And we can even evaluate its energy of deformation. Some other calculations were performed. You can see this works. I just want to mention that if we see dihedral angle of hydrogen peroxide molecule with respect to calculation around nucleic bases of DNA. And we can see here two positions, here and here, where our peroxide is significantly deformed. We can see this isolated angle here, and we can see these values in different positions. But here, almost it is very, very deformed, this angle. So this was some, because I have no time, I will come to conclusions. So I want to say to you, if you want to calculate something using quantum chemistry methods, first you must think what exactly do you want to calculate, exactly do you want to gain as a result. And so you must find suitable method, suitable basis set, maybe suitable if you use DFT is correct and the best functional. So you must ask questions, and especially you can ask in internet. There are many forums on ResearchGate. There are discussions. You can say, I want to calculate some system. What basis set should I take, or something like that. Then you should carefully determine your methods and basis set. It can be some methods. You can just make simple calculation to evaluate some starting point of more careful calculation. There are many schemes, many different methods you can use, and then calculate. But if you calculate something with quantum chemistry, I will strongly recommend to use external computational facilities, such as clusters, some networks, some external, because if you try to make calculation on your notebook or laptop, it will be melted down, I think. It is very heavy. It can be heavy for small computers, these methods. And then you gain your good results. And also, I should say about some remarks. These remarks, they include what I didn't tell in this talk. So I had some time and I talk about some, for me, crucial points, but there are many more crucial points in quantum chemistry. And I admit that I didn't say anything to you about geometry optimizations. I mentioned this, but I didn't tell how this can be performed, and I didn't tell you anything about charges. I didn't tell you about molecular orbital analysis, especially this HOMO-LUMO gap. HOMO is highest occupied molecular orbital. LUMO is the lowest unoccupied. This is first virtual. And this gap we can analyze and have many. Also, I didn't tell you anything about frequency calculation, but they are very important. This is a piece of work about transition states, about nuclear magnetic resonance. And I didn't tell you even about software to visualize your results. Why I didn't tell you about this? Because for me, I used 4 or 5 different softwares, and I dislike them all. So I don't want to tell you something because I myself is uncertain in this case on that moment. And thank you. That's all. Thank you for your attention.
Thank you very much, Dmytro. Let's thank our speaker. And now we are open for the questions. Please, if somebody wants to ask, yes, Bogdana, please.
During your presentation, you told that DFT is a certain method and hydrofoc it's approximation. Yes, but I would like to ask which of this method in the end of calculation give more accurate result?
DFT. If we compare just to simple Hartree-Fock scheme, then DFT, I will tell you. But if we use some post-Hartree-Fock methods, there I can't say as certain. But DFT, I think it will be better than simple Hartree-Fock.
I see. So it means that it's more cheaper in the meaning of computer time. Hartree-Fock method.
More cheaper to use Hartree-Fock?
Yes.
No. I suggest you not to use Hartree-Fock for cheaper. You should maybe take a smaller basis set, but not Hartree-Fock. Or some maybe another method, but Hartree-Fock is, how to say, is not the best method, let's say.
Okay, thank you.
Okay, other questions? In our conference hall, no. In Zoom, probably, please raise hands. Who wants to ask, please? Okay, probably the participants are thinking about questions, and I would like to ask just maybe philosophical question, but it is interesting. So in all the calculations, you use always Schrödinger equation, and for all type of elements.
Yes.
Can we use Dirac equation for this case?
Maybe.
Maybe.
We must have a scheme of how to solve this. We must know. If we can,
it's the same scheme.
If we can, but I don't know what will be the result. I can't say.
Yeah, probably somebody use. I don't know. So
maybe if we can implement these methods into Dirac equation, maybe. So I can't say with certainty, but maybe.
Okay, Okay. Thank you. Do we have other questions? We had a very detailed lecture.
I tried for students.
And yes, it was really interesting. And as for me, I asked during the lecture some short questions, and it was systematic and really interesting. So let's thank Dr. Piatnytskyi once again.